Today we are talking about kinetic theory and the assumptions that go with it. First assumption is that matter is made up of tiny particles. Those particles are in constant motion. And particles undergo elastic collisions when they hit each other or any other object.
Pressure exerted by gas is due to these elastic collisions of the gas molecules against the wall of the container. That's what pressure is. These collisions of each little tiny particle hitting the wall of the container, making a force, a pressure. Equal temperatures, equal pressures, equal volumes. So cool. Avogadro's law says equal volumes of gas at the same temperature and pressure contain the same number of molecules. This is how that guy, Avogadro, Italian, came up with his favorite number, Avogadro's number. A lot of people say to me, hey, what is temperature then? Well, temperature is the measure of the average kinetic energy of a gas molecule. Kinetic means motion, and the average motion of that temperature is what heat is. That's what heat is. If there's no heat, there's no temperature. Zero heat, zero temperature. It's a place that I want to be. It's a place that I don't want to be because it's really, really cold. The higher the temperature of the gas, the faster the molecules are moving. You could almost say the higher the temperature of anything, the faster molecules are moving. If you look at an ice cube, it's really, really cold. Those molecules are not moving. But take it out and put it on your stove. See what happens to it. Well, just the other day, I took an ice cube and I put it in my refrigerator by mistake, and I came back and that ice cube had melted all over the counter inside the refrigerator. It melted all over the shelf inside the refrigerator, and I had water. The molecules in that ice cube went from vibrating to moving around. They were unable to hold its shape anymore. I put it on the stove and then I heated it up. The molecules got faster and faster and faster and went into a gas. It also got more kinetic energy and hotter in temperature. On average.
Faster the molecules move, the more collisions they undergo. This results in more pressure exerted by the gas.
Now you may not be able to see this on the video, but here we have a Kelvin temperature scale, here we have a centigrade temperature scale, and here we have a Fahrenheit temperature scale. And of course, we also refer to centigrade as Celsius. Well, Fahrenheit temperature scale was of course created because this guy Fahrenheit said, look at this, oh my gosh, water freezes at 32 degrees, what a great number, I just pulled that out of the air. And I said, wow, I'm going to heat this thing up and then it's going to go into gas, and I'm going to say, wow, water goes into a gas at 212 degrees, what a great idea. Celsius said, why don't we use the metric system and say water freezes at 0, good idea, and it boils at 100, and we'll just break that up into 100 equal parts, and we'll call it centigrade. We call it Celsius in honor of Celsius. This is a metric system. Kelvin said, no, wait a minute, guys. When it gets really, really cold in my house, I don't move around very much. So when it gets super cold, all molecular movement stops. When all molecular movement stops, we'll call that 0. That's absolute 0. And to equate that to centigrade, it's minus 273. When water boils, it boils at 373 Kelvin. That's because Kelvin is centigrade plus 273. As you can see here, Kelvin does not have a negative sign anywhere in its scale. So we need to use Kelvin whenever we do gas calculations. Boyle's law. What did Boyle's law say? Boyle said, if a volume of gas decreases, then the pressure increases. Here is an example. This volume is decreasing, which means the volume of the container is getting smaller, but the number of particles are staying the same. The number of molecules are staying the same in that same volume. This volume is getting smaller, then the pressure must go up. What did Boyle say? Here's Boyle's name up here. Boyles said volume and pressure. Volume and pressure. Boyles is volume and pressure. If you talk about temperature, it's not Boyles. What gas law is used to explain volume and pressure?
Boyles!
That's right. Good call, Tovin. The opposite is true with Boyles. If a volume of a gas increases, then the pressure decreases. Now this means we have the same number of molecules and we increase the volume that it's in. We increase the container. Then of course the pressure will go down. More formally, volume and pressure of a gas are inversely proportional. It assumes that the number of molecules of a gas and the temperature remain constant. If the temperature remains constant, then the temperature falls away from the calculation. Say, Cassidy, can you give me the formal saying of Boyle's law?
Volume and pressure are inversely proportional.
That's right, volume and pressure are inversely proportional. Good job. You know, you've just earned the word of the day. And let me call in my helper. Take your burden.
Today, the word of the day is Boyle. Text or email or put a comment below.
Like and subscribe.
Like and subscribe and put your gloves on.
Now we know the word of the day is Boyle. Let's look at mathematically Boyle's formula, which goes something like P1 V1 equals P2 V2. This means the initial pressure times the initial volume equals the ending pressure and the ending volume. Pressures are usually given in. It doesn't matter what unit it's given in, but the units must match. So if we're using centimeters of water, then both pressures must be the same. If we're using millimeters of mercury, then both pressures must be the same. Volumes, their units must also match. We often use milliliters, and we also use liters. But if your initial volume is given in liters, then your ending volume will be in liters. Many times your initial volume will be given in liters, and the question will ask, what is your volume in milliliters? Remember to convert to milliliters at the end.